Okay, thank you very much for the introduction, and thank you all for being here. It's my great pleasure here to give you a talk about my recent research. A very nice city, and actually my first time in Canada. So great pleasure. And today I'm going to talk about something about gravitational waves from dynamical channels based on some recent work I've been doing with Lisa Randall also at Harvard. And the whole motivation of our work, you might ask, we are originally particle physicists, why do we care about gravitational wave? Of course, it's about the LIGO discovery. I'm sure this picture you have seen multiple times. But as particle physicists, we like to draw everything in terms of Feynman diagrams, our particle physicist nostalgia. Here we have a binary black hole we have already known from LIGO, and they rotate with each other and radiate gravitational wave and collide at the end. And we collect this gravitational wave and reconstruct the mass, the distance of the informations of the black hole binaries. And after this is done, a very big question is left, that is, how the binary was formed at the first place. So this turns out to be a very difficult question for everybody. So I'd like to attack this question in this talk from several ways. First, of course, people say there are in general two ways to make binaries. Either they evolve in isolation through something like a common envelope, or in dynamical channels where you have multi-body interactions. And I will briefly talk about these two channels. And then I will show you some observables in the waveform of gravitational wave where you can use to tell the difference of channels. And thirdly, I will talk about some exotic signatures we find quite interesting, which may be very useful on top of the observables like eccentricity to tell different channels apart. So as I just said, it is very difficult to tell the formation channels to form binaries because gravity is very weak. So we cannot rely on gravity waves only to form a compact binary. They radiate very slowly, and the orbital distance shrinks very slowly. So if you want typically a 10 solar mass black hole to merge with another 10 solar mass black hole within a Hubble time, then you may already know you need to put them to a very small distance like 1.1 AU initially, and then they can radiate gravitational wave and to merge in Hubble time. The question is, how can you put two black holes to such a small distance? This is a super tiny distance compared with the size of typical giant star, for example. So how can this be done? We know that there's a lot of binaries, and the question is, how will you make this compact? Traditionally, people say you can do this through the so-called common envelope evolution, where you have two stars to begin with. Here I am plotting the gravitational potential of the two stars. And you can see that once one star goes into the red giant phase, then the matter ejected from the star will fill one gravitational well, potential well. And once this is fully filled, it can go into the second potential well. And you are left with a common envelope like this. Things happen here is that there will be dynamical frictions between the matter and the core of the two stars. And this can produce effectively a drag force between the two mass core, and this makes two cores very close to each other. Here you need some very dramatic shrink of distance, maybe from 10 AU-ish to like 0.1 AU, which people claim that is achievable. On top of that, there's a downside of common envelope, which is supernova kicks. That is, if you want to make black holes or neutron stars at the end of the evolution, you have to have this supernova explosion, which is in general quite asymmetric, meaning that you will you will inject a very large velocity to one of the binary member, and this can easily disentangle the binary. So there will be a reduction of the rate. And at the same time, people also talk about the so-called dynamical channels. Here, I imagine we have two black holes, for example, to begin with directly instead of two stars. Then these two black holes somehow interact with a third body. You may say, okay, this kind of three-body interaction is quite rare because it's difficult to encounter a third body. But this is possible if you are in a very dense environment. Then, in this case, the gravitational interactions between the third body and the binary system can sometimes take some energy out of the binary, and binary separation will be reduced and eventually merge. This is a basic idea of dynamical channel. And I just said that you rely on some dense environment to increase the probability that a third body can be seen by the binary. And actually, this kind of problem has been, this question has been asked by James Jeans exactly 100 years ago. So the question he asked is, what will be the thermal equilibrium distribution of binaries bounded purely by gravitational interaction? And he derived the distribution of the binaries in this way. So we know that binaries are characterized by two geometric quantities. One is a separation, the other is a eccentricity, how elliptical the orbit is. And here we know that the separation is directly related to the energy of the binary. So I can express their distribution in terms of energy and eccentricity. Let's look at the energy distribution. This looks like a very good-looking thermal equilibrium distribution because you have the familiar Boltzmann suppression factor for large E. But one thing we should be aware of is that for a bounded system, E is negative. So instead of a suppression, here you actually have a huge enhancement. And on the other hand, on the other side, this funny E factor also make the distribution explode. So which means that the binaries can never reach thermal equilibrium. The distribution diverges in both directions. So what does this mean? This basically means that in a very dense, frequent interaction environment, a very hard binary will become even more harder, and the soft binary will be even more softer. So much for the energy. Eccentricity, this is so-called thermal distribution, which says that you have a flat distribution in E squared. So E0 corresponds to circular one, and E equal to 1 is very elliptical. So typically in dense environment, you will have some very eccentric distribution. So is a dynamical channel in dense environment. There's another way to make three-body interactions. That is, you begin directly with triples. So people know from observation that maybe 20% of stars are in triple system. So we also know very familiar triple system, Sun, Earth, and the Moon. And we call this kind of triple hierarchical triple. Hierarchical means that the distance to the third body is much larger than the binary separation. So typically only in this case, the triple system can be stable. Otherwise, it is in general unstable. And where can we find this hierarchical triple? Maybe in the field we have a lot of triples, and in dense environment we have binaries. And binary scattered with binary can also produce triples. So these are two main channels people talking about when form very compact binaries. Before talking about these channels in more detail, let me just show you a very unprofessional and confusing compilation I made for different channels. So previously, if you remember, when the first gravitational wave signal is detected, there is a implied merger rates ranging from roughly here to here, 2 order of magnitude. And now with LIGO 01 and 02 run, this uncertainty has been reduced to within 1 order of magnitude, pretty impressive. And compare with this observational thing, we have the theoretical predictions from 2 channels. One is a common envelope I just mentioned. The other is dynamical. And in dynamical channels, I can imagine we have 3 stars, the field triples in the fields. And also there are dynamical process in the in globular clusters where you can have genes-like distributions. And also in galactic nuclei or EGN, where you can have a binary close to a supermassive black hole. Supermassive black hole will play the role of a third body, and you can do your triple system stuff. And I said this is very confusing because I must emphasize here that these different bars and dots correspond to different models of common envelope. So the prediction of common envelope actually ranges from here to here, and you should never sum up all these things. On the other hand, the predictions here in the dynamical channel are independent of each other. So it is possible that some of this or all of this contribute together. So it's possible to sum some bars here together to be consistent with LIGO. And I'm not sure how serious you should take about these theoretical predictions, but the general message is that it is possible that binaries observed by LIGO can be formed either in this way, or both, a fraction of dynamical, fraction of isolation. And question is, how can we tell them apart? Okay, then before addressing this question, I would like also to ask this question. So whether there's any relevance to fundamental physics, because we care not only about astrophysics, but also fundamental physics. And nowadays, we feel that we can learn a lot from astrophysical observations about a lot of very fundamental questions in nature, like dark matter, dark energy, and so on. So what can we learn from this channel discrimination about fundamental physics? And now I'm trying to stretch myself a little bit just to provide some motivations. So for example, people say that binaries in LIGO can be primordial. So they are formed in a very early stage of cosmic evolution. In that case, there can never be a common envelope phase. So if you can assemble some primordial black hole pairs, they have to be done dynamically. But there are some caveats about this. You can do this in radiation domination, in which case the plasma around can play a role of the common envelope in some sense. And another thing I want to emphasize here is that the gravitational wave observables we see in LIGO or in LISA in the future may be dependent on the density profile where the binary lives. And this density profile can be sensitive to the nature of dark matter. So there may be some useful information to be learned from binaries about dark matter. With this said, let me show you some observables that are very useful to tell the channels apart. So people in general talk about several observables like spin alignment, eccentricity, the mass function to tell different channels. And in this talk, I will mostly focus on eccentricity, but now I would like to say a bit about general things. So first, spin alignment. In common envelope evolution, in general, the two the spins of the two black holes tend to be aligned with each other, simply because you have the tidal lock from the cloud around. But in dynamical channels, since the two black holes can meet each other very randomly, so it will expect some isotropic distribution of spin. So in that case, you can have large spin misalignment. And how can we tell the spin alignment in a waveform of gravitational waves? The signature will be if you have a large spin misalignment, then you will see a modulation of the overall amplitude in the gravitational waveform. This is because in that case, you will have some angular momentum exchange between the spin of the individual black hole and the binary. And in that case, the mass quadrupole will be affected, and we know gravitational wave is nothing but a manifestation of the mass quadrupole of the system. Similarly, for eccentricity, we know in isolation channel that most of binaries will be very circular. This is because gravitational waves carries away energy and also angular momentum, and we know that angular momentum is eccentricity. So gravitational waves not only reduce the size of the orbit, but also circularize it. So by the end of the evolution in LIGO window, everything will look very circular. But for dynamical channel, you can have some funny interactions between the binary and third body, and I will spend a large fraction of my talk talking about this dynamics, show you that you can have significantly large eccentricity generated in this channel. And how would you see eccentricity in waveform? Well, this is Kepler's law. You know that once you have an elliptical orbit, and the velocity will not be uniform. So you will be faster at the periapsis. So you will have higher harmonics in mass quadrupole. And you will have higher harmonics in gravitational wave. So by looking at these harmonics, you can measure the eccentricity. Just to put this more quantitative, energy and angular momentum of the system are related to the separation and eccentricity E. This is boring high school Newtonian mechanics. But the thing we can learn from this is that if we turn on gravitational wave, and we know how gravitational wave will carry away energy and angular momentum, then we will know how A and E get reduced by gravitational wave. And there will be a certain one-to-one relation between A and E described by this GE function. And now I invite you to remember this. This will appear several times in my talk. Not this number, but I mean this shape. This shape is very useful. So how to understand this? So vertical is the separation. Horizontal is eccentricity from 0 to 1. Now, the message is that in typical evolution, you'll have to reduce the orbital size by many orders of magnitude. So if you begin with a general point on this plot, general means anywhere from here to here, not too small, not too large. Then by several orders of magnitude reduction in vertical direction, you are in general end up with tiny eccentricity. So this is why you would always expect circular binaries from isolation channel. But I will show you later that in three-body channels, sometimes a third body can kick the binary to this range. So even by many orders of magnitude reduction, you can still have some finite E that you can observe through gravitational wave. And this plot just shows you the radiation power of binary as a function of E with separation fixed. So you will see that if you have a circular binary, then you will only have quadrupole radiation, the typical quadrupole nature of gravitational wave, because graviton is spin 2. And when you increase the eccentricity, you will have higher harmonics. And you also notice that the power is greatly enhanced for large E, simply because for fixed semi-major axis, you will have much smaller periapsis distance for large E, and this will boost the radiation of gravitational wave a lot. Okay, now I'm going to some detail about the triple system thing. Yes.
For the current generation of LIGO, is it only sensitive to the second harmonic?
Why? So LIGO is sensitive to a frequency range, as long as you are in this frequency range.
I guess I mean in the signatures that LIGO is seeing, do they have enough potential ability to see signals in other harmonics at present?
Well, you rely on the template. If you have template, yeah, or you can do a burst search. So high E looks like a burst.
LIGO only gets 0, and they don't have to.
But once you have templates, LIGO people claim that they can reach precision like 0.01. Yeah. But nowadays, what I know is that they can make template up to 0.4 in E. And beyond that, there's no. Yeah. Okay. Three-body thing. If you can believe me, this is just a very simple Hamiltonian describing 3 point particles interacting through gravity. And I deliberately reorganized this Hamiltonian into several parts. So the trivial motion of the barycenter of the triple. Here is the motion of the small binary, which I call small binary, the binary that will merge. And there will be a large orbit which describes the small binary plus a third body. And that will be interactions. The interactions describe the interactions between the small orbit and the large orbit. And so here the hierarchical triple actually helps us a lot, because in general we know a three-body system cannot be solved completely. But since we have a hierarchical triple, we have a small parameter, a distance between the ratio of the small orbit separation over the large orbit separation. In this case, we can do a small parameter expansion. And if we keep only the leading term, which is quadruple, we are talking about a quadruple approximation. So be careful, this quadruple has nothing to do with the quadruple nature of gravitational wave. But this leading order interaction is not very useful because it is described by the location, in terms of the location of the three bodies, which we don't quite, we are not quite interested in. What we are actually interested in is the long-term evolution of geometric quantities like orbital distance and the eccentricity. So the thing we do is that we integrate out the fast motions of the small orbit rotation, large orbit rotation. And we are left with a so-called low energy Hamiltonian described purely by geometric quantities. So here you don't have to care about k is a constant. And W here is made of the inclination angle between the small orbit and the large orbit, the eccentricity of the small angle, and also the position of the periapsis of the small orbit. So the funny thing of this expansion is that there are some accidental symmetry we realized in the leading order, at the leading order. So of course we have the total energy and total angular momentum conserved, but on top of that, the leading order interaction tells us that the energy of two orbits are also separately conserved, meaning that the separation A1 and A2 are also conserved. And also the magnitude of the J2, the angular momentum of the large orbit, is also conserved, but the direction is not. So we know that A1, A2, the separation of the two orbits, and also the eccentricity of the large orbit will be conserved in this leading order interactions. So to put these words into a diagram, let me show you a triangle formed by the angular momentum. So total angular momentum, the gray line is conserved. And the large angular momentum is conserved in magnitude but not in direction. So it can move on a circle. And to form a triangle, you will realize that the angular momentum of the small orbit can sometimes be large, sometimes be small, as long as you begin with a very large inclination angle. So a large inclination angle will turn into a large eccentricity for the small orbit. So this is a so-called Kozai-Lidov mechanism. People studied this back in 60s when they studied artificial satellite. And nowadays we realize this can actually happen in many places. But I should say that until now, several tens years has passed, but we have never seen a real system where Kozai-Lidov is directly manifested, is directly seen in time. So I will show you that gravitational wave has a potential to see these Kozai-Lidov oscillations directly.
So we see asteroids. There are asteroids which are in Kozai.
Yeah, we have evidence that a lot of things KL is happening, but we never see that oscillations in. We were told that there's one system of triple pulsar where you might have, but people haven't finished analyzing the data. So that might be one system. Otherwise, okay, then with that said, what you need to do is just solve your equation of motion from that Hamiltonian. And equation of motion is trivial. I don't want you to read the details, but only the colors. So the color here, so it's basically time evolution of all geometric quantities, separation, eccentricity, angular momentum, the position of periapsis. But the message here is that Kozai-Lidov, which is derived purely from Newtonian dynamics, described here by the black color. And on top of that, we need to add post-Newtonian corrections, GR corrections, which is very important for gravitational wave. So firstly, you will have the precession of the orbit, which we are familiar from the Einstein time. And also we will have back reaction from gravitational wave. And a simple way to look at this equation is to realize that the three colors actually correspond to three very different time scales. So at early time, the GR post-Newtonians are not important at all. So everything is dominated by Newtonian dynamics, by the Kozai-Lidov thing. So Kozai-Lidov time scale is always the shortest. So if I plot the orbital separation as a function of time, I will see oscillations in early time. But later on, the orbital size will be reduced. And you will have important PN correction or gravitational wave. So PN correction tend to interrupt your Kozai-Lidov resonance. So it suppressed oscillation somehow. And eventually it will merge as if they are in isolation, because at this stage, the binary is already so hard that you can never feel a third body. So based on these observations, what we have been doing is that we derived an analytical formula, just to save you some time, to predict the eccentricity in LIGO directly from all initial conditions of the triple system. You can say, of course, we can also run your code numerically to trace the evolution, but this can be numerically expensive if you have many cycles to do. If you just want some theoretical estimate of how large eccentricity can be, this is a very simple formula where G is a function I mentioned before. And actually, it appears here again. Here I am plotting the same evolution I showed you in the last slide. the separation and eccentricity, but in A and E plane. So originally you have many oscillations, but no effective reduction in A. And later on, gravity will become important. You will have circularized thing. So here's a comparison between the numerical and our analytical formula. Works pretty well for small eccentricity, which is a dominant thing, but fail at large eccentricity where a non-perturbative effect will be important. And we put these formulas in use for several channels, like in galactic center, where we know that the perturbation theory will work well. So in this case, the final eccentricity will be very sensitive to the distance to the supermassive black hole, and thus very sensitive to your mass profile. And people know theoretically that stars in the center of galaxy will form a Cuspy distribution if the galaxy is fully relaxed. But to my best knowledge, this Cuspy distribution has never been observed directly, and people tend to see a more core-like distribution. We don't know why. Maybe just because the galaxy is not fully relaxed or some other reasons. Of course, if you want to apply this analysis to galactic center, which is very dense, you also need to take into account scattering of your binary with surrounding stars, which cause evaporations. So with all these things considered together, we can use our analytical formula to predict the final eccentricity in LIGO at 10 Hertz. Roughly, you can see this distribution will be sensitive to your mass profile in the galactic center. And there will also be important correlation with other parameters we can measure. This will be very useful information to tell different subchannels. But if you look at these numbers carefully, you may say I'm cheating because I have already told you that LIGO people claim they can measure eccentricity down to 0.01. So this is log scale. 0.01 is here. So LIGO will be able to resolve things only to the right of this, the tail of the distribution. They can never resolve the whole shape of this. But hopefully, we can do this in LISA in the future, simply because LISA observe binaries at a very different frequency range, low frequency, where the binaries have not fully circularized.
Well, I guess this is maybe only relevant to the rightmost part of your distributions. But have you checked how well your analytic formula stands up against just brute force?
Yeah, we did.
Brute force, ensemble, orbital integration.
Yeah, we
in one case.
yeah. In this case, agreement is not very well.
Well, I understand that,
Yeah.
that this is a particular case. I'm talking about just the whole ensemble, right? Where you have a wide range of initial conditions. I know
Yes.
it's sort of a bit painful to just do all the orbital integrations, but it's not
Yeah.
computationally outrageously expensive, right?
Right. So I mean, if you can calculate eccentricity well enough, you can always recover whatever you have through simulations. Yeah. And we can do that for small e, for a large fraction of binaries. So most of this, if it is larger than 0.1, we cannot do very well. Okay. But in the future, like in LISA, the peak will be the most important thing. So because LISA will observe at 0.01 Hertz, so it moves 3 orders of magnitude in E. So E is almost linear in F. So you move your ability from here to here. You can see the whole thing. And LISA, people doing LISA claim that there will be maybe up to several hundred or even several thousand stellar mass black hole binaries individually resolvable in LISA in 4 or 10 years. In particular, the first event seen by LIGO could actually be seen in LISA if LISA was turned on several years ago. So this is the plot where you have a lot of binaries in LIGO. If you extrapolate this backward in time, you will recover that in LISA. This is our some preliminary study about how LISA can see eccentricity. And the galactic center distribution I just showed you is here, a single curve. Together with this, I also show you some other channels predicting different E, peaked at different position, very small E0 at 10 Hertz. But by the time they enter the LISA window, typically the E will get enhanced a lot. So if you are only sensitive to circular binaries in LISA, you can already learn a lot. For example, if everything is in this channel, then if LISA can only measure things below 0.01 in eccentricity, basically you will see nothing in LISA. So we call this measure eccentricity without measuring eccentricity, because you can count circular ones. If circular ones are significantly less than what you expected, then you know something. Of course, if you can extend this to higher E by templates like 0.4, you can recover a lot of dynamical ones in LISA. But one very important thing, actually two very important things when we talk about LISA measurement is that the eccentricity not only gets enhanced in LISA window, but also it will affect the intrinsic distribution of binaries and also the signal-to-noise ratio of binaries in LISA. So signal-to-noise ratio, nothing but the power divided by your noise. And in the case of eccentric binary, we know there will be a lot of higher harmonics. And again, this can be difficult to do if you really want to sum over all the higher harmonics. So we just have a very simple formula for SNR if you want to do a simple estimate, which agree perfectly with numerical calculation. So it's a simple scaling, meaning that a large E tend to suppress the signal-to-noise ratio. But on the other hand, the intrinsic number density of binaries will get enhanced by eccentricity for fixed merger rate in LIGO. Why? Because with fixed merger rate, you need to arrange a certain number density with certain merger time to reach that merger rate. And what I can tell you here is that the eccentricity tend to slow down the merger process. You may say this is quite counterintuitive because I just show you the eccentricity will greatly boost the merger for fixed semi-major axis. So the important thing here is that it is not the semi-major axis that you should fix. It is a frequency of radiated gravitational wave that you should fix because you observe binary at a certain frequency. If you do this, you will realize that the peak frequency of a gravitational wave will be dependent not only on the binary separation, but also on the eccentricity. So here, epsilon E is 1 minus eccentricity squared. And in this case, you will see that you will have a much higher peak frequency compared with the orbital frequency. So in this case, if you fix the peak frequency, then you will delay the merger if you have a large eccentricity. A delayed merger will require you to have a large number density to match a certain merger rate. So in this case, actually, you will be able to see more binaries than you expected if you have mildly large E. But for large E, of course, due to the suppression of SNR, you will always see less. So much for eccentricity distribution. In the last several minutes, I don't know how much time I have. I can, 15, okay, cool. I'd like to describe some fun thing we have been doing. That is, we look for some new signatures, exotic signals beyond the traditional measurement of eccentricity, spin alignment. So first thing is that if, yeah.
Clarify, there's one thing I couldn't sort it out myself. So you talked about the hierarchical triples,
Yes.
Hamiltonians, and also
Right, yeah.
well. And then you make a jump to put them into cluster of like the center environment with density.
Oh, I'm sorry, yeah, I was not clear enough. I'm imagining the supermassive black hole as the third body.
Okay.
Yeah, so it's still
And then the primordial, there are primordial binaries.
not necessarily primordial.
The binary which will form in the cluster in the galactic center environment by hardening from scattering.
Yes. Actually, the hardening can be done by KL itself. Once you have large E,
So you need a primordial, and you need a sort of
you need binary, yes, yes.
That came from the scattering of few stars.
Well, I guess we have binaries at the center of galaxies. I don't know. And if you are in the center, you can also have some replenishment of binaries from outside through relaxation. And this is more efficient for black holes because black hole is more massive than stars. Yeah. Okay, any other question before I? Cool. So the first thing we can think about when we talk about triples is that if we really have a binary in a triple, then we can do something similar to binary poser. The idea is that the radiated gravitational wave simply get Doppler shifted by your orbital motion around the third body. So in this case, if you monitor the frequency of the gravitational wave as a function of time, you can do a similar observation like you do for binary poser. So here, the binary system will look the poser you are looking at, that emitting pulse. And the third body will be like the invisible counterpart of the poser. And if you can do this for several years, you can do very, I cannot say, you can do measurement about orbital parameters of outer orbit, large orbit. And just to give you a sense of why this can be done, I just put some typical numbers here. In typical galactic center, you have million solar mass of a black hole. And if you are 100 AU away, which is people are talking about for KL channel, and the orbital period of a large orbit is simply 1 year. So if you turn on LISA for 5 years and look for such monitoring such a system, you will see several complete cycles. And the Doppler shift in this case is huge, 0.01 speed of light. So much beyond your sensitivity of frequency. And this is very cool because we see that the period of this outer orbit is directly related to the mass density enclosed by the binary. So this is actually a direct probe of the density. So I mentioned before that we want to learn not only the binary itself, but also the surrounding environment, the density profile. And this kind of measurement can be a useful way to do that. And of course, if you want to do this more realistically, there will be a lot of degeneracy. Like if you are quite far away from the third body, then your period will be very long, much longer than the LISA mission. In that case, you can only measure a small fraction of orbit. And of course, you can play around and see a lot of degeneracy, for example, between the velocity and the period. And here is just some boring Fisher analysis to show you that in typical galactic center channel, for the frequency range of LISA, we will be able to leave this degeneracy to a certain distance to the third body. So here it is like 1,000 AU, roughly the same region people talking about for KL channel. And also there will be important degeneracy. I should. So this is degeneracy between the period and the velocity. And more importantly, there will be degeneracy with the chirping. Because if you see a small enhancement in frequency during time evolution, then this can be either from your orbital evolution or from the chirping. So if you cannot measure chirp very well, you will have a large degeneracy. And this just shows you in which range you will be sensitive to either one. And another cool thing, I think, even more interesting is to, I mentioned this, to look for eccentricity variations directly in LISA. So in this case, I already showed you this plot before. You have oscillations of eccentricity in the early time. And if you plot the peak frequency of gravitational wave for this typical example, you will realize that you will have very funny shape of radiated gravitational wave frequency, and which sweep all the LISA channel from millihertz to 0.1 hertz. And for this to be observable, it is very important that this time duration of this oscillation is comparable to your LISA time. So we also do this. For typical range, this is just several years, perfectly match the LISA time. And if you plot the frequency spectrum, you will see a shape like this. If you remember, in typical LIGO events, or even in LISA, most of binaries will do a normal chirping with single increasing frequency. So this will be a very distinct signature. Even you cannot resolve the whole thing, if you can see a increasing in eccentricity, this will be a smoking gun signature of Kozai leadoff, because otherwise you have no way to increase eccentricity. In this case, we are talking about a very eccentric system, and I mentioned before that the signal-to-noise ratio will be greatly reduced for very eccentric ones. So why can we find these binaries? The answer is that in this case, we will also have greatly boosted number density to the extent that there will be maybe several events in the Milky Way. So we can look for very nearby events exhibiting Kozai leadoff oscillations in Milky Way. And on top of this, I need to mention that LISA people also talk about we can resolve individually like 25,000 binary white dwarfs in Milky Way. And I can imagine that maybe a fraction of that are also in triple system. And if you are in triple, there may also be Kozai leadoff resonance that you can try to learn. But white dwarfs are more complicated stuffs than neutron star or black hole. So maybe this is something interesting to do in the future. Okay, it's about the time. So let me try to summarize. So the general take-home message is that stellar mass black hole binary we see in LIGO could be formed dynamically. And the way to tell whether they are from isolation or from dynamical channel, you can do different things like eccentricity, spin alignment. And in addition to that, you can also look for more interesting signals like barycenter motion, induced Doppler shift, and also eccentricity. And all these things will be very important to understand not only the formation channel, but also the ambient environment of black hole binaries. Okay, thank you. Yes.
Well, I have a hierarchical triple involving binary black hole in a dense cluster.
Sure.
Can one really realistically expect Kozai oscillations to be taking place given that the outer star is likely to be perturbed? by encounters with other stars in the binary?
Yeah, that's a very important thing. So most of the triple cannot be very stable in clusters. Only those survived can. So this will reduce the number. Yes. So the typical situation in cluster is that non-perturbative things, non-secular evolution will be dominant. So that's why we choose to study galactic center first, where perturbation theory hold well, because the cell body is so massive, it's very stable.
Well, there are no other questions. Then let's thank Zhong-Zhi again.
Thank you very much.